So I want to start off this video by doing another little bit of a thought experiment. I want you to imagine taking a piece of metal and a glass of water, and we're going to put them directly in the sun. And then we're going to wait a little bit of time. We'll come back, and if you were to feel each of the substances, you would note that the piece of metal feels a lot hotter than the water. And what you're actually observing is something known as the specific heat capacity of that substance. Not every substance responds in the same way to added heat. Some get a lot hotter, their temperature changes is more drastic. Others with the same amount of heat don't change their temperature very much. And so if we were to kind of let's take a piece of iron metal, and we'll take exactly 1 gram of it. And then we're going to take some water and take 1 gram of it. And to both of these, if we were to add 8 joules of energy, that iron metal would get up to about a temperature of about 41 degrees Celsius, assuming we start at 25 degrees. Forgot to mention that. But that water, with the same amount of energy, same mass, would only go up to about 27 degrees. So its temperature would only raise a couple of degrees. And this is, including that little thought experiment we did, is a demonstration of what's known as specific heat capacity. This is a property of a substance that basically is what is the energy required to increase 1 gram of a substance. Actually, I'll got a little bit there to increase the temperature of 1 gram of a substance by 1 degree Celsius. And every substance has a different specific heat capacity. So this is just a small table here. I don't want you to memorize this, but you can kind of see here the difference between, say, water and, go all the way down to like zinc, for example. And what this basically means, the larger the value it is, that basically just means it requires more energy to get hotter. So if I were to supply 5 joules of energy to water and 5 joules of energy to zinc, that zinc metal would increase its temperature by a whole lot more than water would. And the way specific heat is calculated and represented. So we use this capital letter C for specific heat. It's equal to heat. So there's the lowercase q, heat in joules, divided by the mass times the change in temperature. So mass is in grams, and temperature is usually in degrees Celsius or in degrees Kelvin. We haven't talked about Kelvin yet. We will eventually, but they're interchangeable in this case. You won't see degrees you will not see me giving you problems with degrees Kelvin until we actually talk about it. But if you're looking at some online resources, you might see tables like this, and the temperature unit might be in degrees Kelvin. So it's they're interchangeable for this purpose. All right, so let's look at some problems with specific heat capacity. So we're looking at an example here. Now, the formula we generally use is Q equals mc times delta T. I just rearranged this formula here to solve for Q. So here's our example. We're going to take 1.23 kilograms of iron at 25 degrees Celsius, and we're going to heat it with 823 joules of energy. If iron has a specific heat capacity of 0.449 joules per gram per degree Celsius, what is the temperature of the metal at the end? So let's just kind of quickly diagram what we're doing here. We're taking a piece of metal, so 1.23 kilograms of iron, and we're adding to it 823 joules. And this metal is starting at 25 degrees Celsius. Adding that energy is going to heat it up. So we're not going to change the mass at all. It's still 1.23 kilograms. But what is the final temperature of the metal after adding that energy? Now, in a problem like this, the tactics we're going to use here is number one, which equation are we going to use? Okay, well, it's kind of easy. I kind of gave it to you at the beginning, but this is something where you're going to have to remember, well, I'm using specific heat capacity and I'm adding heat and I'm dealing with temperature. So I need to use this equation. Now, the next thing you need to decide is what is my unknown? Okay, so let's highlight everything here. We're given the mass, we're given a temperature, we're given energy, we're given specific heat capacity. So our unknown here, if this is our initial temperature, Ti, our unknown here is going to be our final temperature. So then what we're going to do is let's rearrange this equation to solve for the unknown. All right, so if we rearrange this to solve for Tf, this is what our equation looks like. And if you don't know how to do this, please come talk to me about rearranging equations. All right, so let's just plug everything in. Our heat is 823 joules. Our mass is 1.23 kilograms. Now I'm going to pause here for a second and see if you can figure out what I need to do with that. What should our units of mass be? I'm going to go back up to a previous lecture here. Mass should be in grams. All right, so first thing I'm going to do, just do a quick conversion. 1.23 kilograms in 1 kilogram. There is 1,000 grams. So my mass should be 1,230. And then I'm going to throw in the specific heat capacity. So it's there highlighted in red, 0.449 joules per gram per degree Celsius. And then plus my initial temperature. All right, now I want to illustrate something to you. Notice I've been keeping track of my units because I can start canceling some things out. Notice the joules cancel out and the grams cancel out. The only thing that doesn't cancel out are the degrees Celsius, which makes sense because I'm calculating a temperature here. And kind of remember your math, your algebra. Um, anytime, so like if you have something like this, if you have a number or a unit that's the denominator of a denominator, that's really saying the same thing, like it should be up top. So just a little kind of review of some math principles. So I put all of this together, throw it in my calculator, keep track of significant figures, and that comes out to 26.5 degrees Celsius. All right, so you should be able to use this equation to be able to solve for any single of the unknowns. I'm never going to give you more than one unknown. You'll be given every single piece of data except one, and you should be able to solve for any aspect of this equation.